Welcome to today's session. In this video, we'll tackle an intriguing problem titled Find a corresponding node of a binary tree in a clone of that tree. This problem challenges us to navigate binary trees effectively, focusing on identical structures and their properties. Let's dive into the details and break it down step by step. In this problem, you are given two binary trees, one is called the original tree, and the other is called the clone tree. These two trees are identical copies of each other in structure and values. Additionally, you are provided with a reference to a specific node in the original tree, which we will refer to as the target node. Your task is to locate the node in the clone tree that corresponds to this target node. It's important to note that even though the target node's value will match the value of the corresponding node in the clone tree, you need to return the actual node object from the clone tree, not just its value. The inputs consist of references to the root nodes of both trees and the target node, and your output should be the corresponding node object from the clone tree. For example, in the first scenario, the original tree is represented as 7, 4, 3, null, null, 6, 19, and the clone tree is an identical copy of this structure. The target node is the node with the value 3 in the original tree. The output in this case would be the node in the clone tree that also has the value 3. Since the two trees are identical, the position of the target node in the original tree directly corresponds to the position of the node in the clone tree with the same value. Your goal is to return this node object from the clone tree. In the second example, the original tree is 1, 2, 3, and the clone tree is again an exact copy of this structure. Here, the target node is the root node of the original tree, which has the value 1. The corresponding node in the clone tree is also the root node, and it also has the value 1. In this case, you would return the root node object from the clone tree because it corresponds to the target node in the original tree, based on both its value and position. In the third example, the original tree is a right-skewed tree represented as 8, null, 6, null, 5, null, 4. The clone tree is again identical to the original tree. The target node in this case is the node with the value 4 in the original tree. The corresponding node in the clone tree is the node with the same value 4 in the same position within the structure of the tree. This demonstrates that the solution must work for trees of various shapes, including skewed trees. Some constraints to keep in mind are that the original tree can have up to 10,000 nodes, all node values are unique, and the target node will always exist in the original tree. Additionally, edge cases include trees with just one node, where the root is the target, and skewed trees, where the target node corresponds to a node deeper within the structure. To solve this problem, we first consider a brute force approach using BFS or DFS traversal. The idea here is straightforward: since the original and clone trees are identical in both structure and values, we can traverse both trees simultaneously. As we progress, we compare the current node in the original tree with the target node we're looking for. Once we find the target node in the original tree, the node at the same position in the clone tree will be the corresponding node. This method is simple to implement, but it has some trade-offs. While the time complexity is O(n), as we may traverse the entire tree in the worst case, the space complexity is O(h), where h is the height of the tree. This is because the recursion stack or queue used for traversal needs to store nodes from both trees simultaneously, potentially doubling memory usage. While intuitive, this approach may not be the most efficient option due to these trade-offs. Now let's consider a second approach that optimizes the traversal process. Instead of traversing both trees simultaneously, we can focus solely on the clone tree by leveraging the identical structure of the original and clone trees. Here's how it works. First, we traverse the original tree to locate the target node. During this traversal, we record the path taken to reach the target node, such as a sequence of left or right moves. Then, we follow this recorded path on the clone tree to directly locate the corresponding node. This method eliminates the need to traverse both trees at the same time, reducing memory usage. However, it introduces added complexity in recording and following the path. The time complexity remains O(n), as we still traverse both trees, and the space complexity is O(h), due to the recursion stack. While more efficient than the first approach, this method can be harder to implement because of the additional step of path recording. For a simpler solution, we can use an even more streamlined approach, a single DFS directly on the clone tree. This method eliminates the need for simultaneous traversal or path recording altogether. Instead, we perform a depth-first search on the clone tree and compare each node's value with the target node's value from the original tree. Once we find a match, we return the current node from the clone tree. This approach is efficient and easy to implement, as it avoids the overhead of managing multiple trees or recording paths. The time complexity remains O(n), as we may need to traverse the entire clone tree in the worst case. Similarly, the space complexity is O(h), due to the recursion stack for DFS. This approach strikes a balance between simplicity and efficiency, making it a practical choice for solving the problem. This problem highlights some key insights. The identical structure of the original and clone trees ensures that traversing one tree is sufficient to locate the corresponding node. Additionally, we don't need to compare values extensively. The guaranteed existence of the target node in the clone tree simplifies the process. Among the approaches we've considered, the brute force method with simultaneous traversal is the easiest to conceptualize but doubles memory usage. Path recording is more efficient but adds implementation complexity. The single DFS approach, however, stands out for its clarity and efficiency. By focusing solely on the clone tree, we avoid unnecessary overhead while maintaining a straightforward process. This is why we chose the single DFS method as our final strategy. It's simple, efficient, and avoids the trade-offs of the other approaches. In this problem, we are given two binary trees, the original tree and its identical clone. We also have a reference to a specific target node in the original tree. Our goal is to locate the corresponding node in the clone tree. The key insight here is that the two trees are structurally identical, and each node in the original tree maps to a unique node in the clone tree. To solve this, we can take advantage of this one-to-one mapping by traversing both trees simultaneously. For traversal, we can use either depth-first search, or DFS, or breadth-first search, or BFS. Since the trees are identical, the target node in the original tree will always align with the corresponding node in the clone tree during traversal. This ensures that we can easily find the corresponding clone node by visiting nodes in the same order in both trees. The algorithm can be implemented using a DFS traversal, and we'll walk through the key steps next. To begin the DFS traversal, we define our input, which consists of the original and clone trees, as well as the target node in the original tree. Starting at the root of both trees, we compare the current node in the original tree with the target. If the current node matches the target, we immediately return the corresponding node in the clone tree. Otherwise, we recursively traverse the left and right subtrees. If the target node is present in the left subtree of the original tree, the corresponding node will be found in the left subtree traversal of the clone tree. Similarly, if the target is in the right subtree, its corresponding node will be in the right subtree of the clone tree. If the original tree is empty, or the target is not found in the tree at all, we return none. This approach ensures that we visit nodes in both trees in sync and locate the corresponding clone node efficiently. The pseudocode here provides a clear breakdown of the DFS traversal process. First, we handle the base case where the current node in the original tree is none, in which case we return none. Next, we check if the current node matches the target node. If it does, we return the corresponding node from the clone tree. If the target is not found at the current node, we proceed with a recursive search of the left subtree. If the target is found in the left subtree, we return the result immediately. Otherwise, we move on to the right subtree and continue the search. This recursive approach naturally uses the call stack to keep track of the traversal path in both trees. While we're using recursion here, an iterative solution could also be implemented using an explicit stack. The complexity of this approach is worth noting. The time complexity is O(n), since every node may be visited once, and the space complexity depends on the height of the tree due to the recursive call stack. The space complexity of the recursive solution is determined by the depth of the call stack, which corresponds to the height of the tree. In the worst-case scenario, such as a skewed tree, the height of the tree could be O(n), making the space complexity O(n). For balanced binary trees, the height is logarithmic, resulting in a space complexity of O log n. Key operations of this algorithm include the simultaneous traversal of both trees, ensuring that corresponding nodes are processed in sync. The base case check is critical, as it allows us to stop further recursion as soon as a match is found, optimizing the traversal. By prioritizing the left subtree before the right, the algorithm performs a complete depth-first traversal. The approach also handles edge cases effectively, such as when the original tree is empty, or when the target node is the root. If the tree is skewed, the algorithm still processes nodes sequentially, demonstrating its robustness. While recursion is a natural fit for this problem, it's important to consider cases where recursion might not be ideal, such as when dealing with languages that have strict recursion depth limits. In such cases, an iterative solution using DFS or BFS can be implemented. BFS, in particular, is an alternative that avoids recursion entirely. By using two queues to traverse both trees simultaneously, BFS processes nodes level by level. This approach may be preferred for shallower trees, as it keeps the traversal breadth first and avoids the potential pitfalls of a deep recursive call stack. The implementation is straightforward. We maintain a queue for the original tree and another for the clone tree, adding left and right children to the queues as we traverse. When we find the target node in the original tree, we return the corresponding node from the clone tree. This iterative approach is equally efficient in time and space complexity, with O, N, time complexity and O, H, space complexity due to the queues. The BFS approach provides a robust alternative to recursion, particularly for scenarios where recursion depth could be a concern. By using queues for traversal, we ensure that nodes are processed sequentially and corresponding nodes in both trees are visited in sync. Despite the differences in how nodes are traversed, the time and space complexity of BFS remain the same as DFS, with O, N, time complexity for visiting all nodes and O, H, space complexity for storing nodes in the queue at any given time. Both the DFS and BFS solutions effectively solve the problem by leveraging the identical structure of the original and clone trees, ensuring that the corresponding node is located efficiently. Understanding both approaches allows for flexibility in choosing the most suitable method based on the constraints and characteristics of the input trees. This implementation solves the problem of finding the corresponding node in the cloned binary tree for the given target node in the original tree. The solution uses an iterative depth-first search (DFS) approach to traverse both trees simultaneously. First, the getTargetCopy method initializes a stack to simulate the DFS traversal. Each element of the stack is a tuple containing the current nodes from both the original and clone trees. The traversal ensures that at every step, the algorithm processes nodes from the two trees side by side, maintaining their structural correspondence. The loop iterates as long as the stack is not empty. In each iteration, the top element of the stack is popped, which represents the current node pair from both trees. The algorithm checks if the current node from the original tree matches the target node. If it does, the corresponding node from the clone tree is returned immediately as the result. If the current node is not the target, the algorithm continues traversing the child nodes. It first pushes the right child node pair, if they exist, onto the stack, followed by the left child node pair. This ensures that the traversal respects the DFS order. Notably, the problem guarantees that the target node exists in the original tree, so the algorithm will always find and return the corresponding node in the clone tree. The return none statement at the end is technically unreachable but included for logical completeness. This approach ensures an efficient O, N, time complexity, where N is the number of nodes in the tree, as each node is visited exactly once. The space complexity is O, H, where H is the height of the tree, due to the stack storage for the DFS traversal. This concise and robust implementation handles the problem requirements effectively while maintaining clarity and efficiency. Here, we start with the implementation of our solution in Java. The method getTargetCopy takes three parameters: the original tree, its cloned version, and the target node we want to locate in the clone tree. To solve the problem, we utilize a depth-first search approach by maintaining a stack that stores pairs of corresponding nodes from both the original and clone trees. Initially, we push the root nodes of both trees into the stack. Then, we enter a loop where we process nodes from the stack. For each pair of nodes retrieved, we check if the current node in the original tree matches the target node. If it does, we return the corresponding node from the clone tree as the result. This ensures that we identify and return the exact node in the clone that corresponds to the target in the original tree. If the current node does not match the target, we continue exploring its children. First, we check if the node has a right child. If it does, we add the right child of both the original and clone nodes to the stack as a pair. Similarly, if the node has a left child, we add the left child of both trees to the stack. This ensures that all nodes are eventually traversed in a depth-first manner. Now, the return statement at the end of the method is technically unreachable under the problem's constraints, because the problem guarantees that the target node always exists in the original tree, and hence it must have a corresponding node in the clone tree. Moving on, we also define the treenode class, which represents the structure of a binary tree node. Each node contains an integer value, as well as references to its left and right children. To facilitate our traversal, we also define a pair class. This generic class allows us to store two related objects together, in this case, corresponding nodes from the original and clone trees. The class provides a constructor to initialize its key and value, which represent the two objects being paired. It also provides getter methods, getKey and getValue, to retrieve the respective components of the pair. This design allows us to efficiently manage and process the pairs of nodes during our traversal. By using this pair class, we ensure that our solution is both clean and easy to understand, while adhering to the depth-first search strategy to locate the target node's counterpart in the clone tree. In this example, we are given an original binary tree and its cloned version. The target node is the one with the value 3, which is a leaf node. To solve this, we initialize a stack containing tuples of the corresponding nodes from the original and clone trees. Initially, the stack only contains the root nodes of both trees, which have the value 1. This stack will help us traverse both trees simultaneously while maintaining the correspondence between their nodes. To start the traversal, we pop the top of the stack, which gives us the root nodes of both trees. Comparing the value of the original root node, 1, with the target value, 3, we see that it's not a match. So, we push the children of these nodes onto the stack, ensuring we pair nodes from the original and clone trees. The stack now contains the left child pair with value 2 and the right child pair with value 3. Next, we pop the node pair with value 2. Again, the value 2 is not equal to the target value 3, and since this node has no children, the stack remains unchanged. Finally, we pop the node pair with value 3. This time, the value of the original node matches the target value. Therefore, we return the corresponding node from the clone tree, which also has the value 3. In the second example, the target node is the root node itself, with the value 1. Once again, we initialize the stack with the root nodes of the original and clone trees. Since the target is the root, we don't need to traverse further to find a match. We begin by popping the root node pair from the stack. Comparing the value of the original root node, 1, with the target value, we find that they are equal. This means we have already found our target. The corresponding node in the clone tree, which is also the root with value 1, is returned as the result. Moving to the next example, we now consider a deeper tree structure where the target node is farther down the hierarchy. Here, the target is the node with value 5. As before, we initialize the stack with the root nodes of the original and clone trees. Starting the traversal, we pop the root node pair with value 1. The value doesn't match the target, so we push its children onto the stack. This adds the right child pair with value 3 and the left child pair with value 2 to the stack. Next, we pop the node pair with value 2. Again, it's not a match, so we push its children onto the stack. This step adds pairs for nodes with values 4 and 5 to the stack. Now, we pop the node pair with value 4. Since 4 is not equal to the target, and the node has no children, the stack remains unchanged. Finally, we pop the node pair with value 5. Comparing the value of the original node with the target, we find a match. This means the corresponding node in the clone tree, which also has the value 5, is our result. In this example, we've demonstrated how the algorithm traverses the tree systematically, ensuring all nodes are checked until the target is found. The clone node with value 5 is returned as the output. Here, we analyze the time complexity of the algorithm. The algorithm uses a depth-first traversal, or DFS, to explore both the original and cloned binary trees. During this process, it visits each node exactly once in both trees. This means the total number of operations is directly proportional to the number of nodes in the tree, denoted as n, resulting in a time complexity of O(n). Breaking it down, each node is pushed onto the stack at most once, which contributes n operations in the worst case. Similarly, each node is also popped from the stack only once, adding another n to the total. Lastly, the logic for comparing nodes and conditionally traversing their children involves constant time operations per node, which, when summed up across all nodes, also results in n. Putting it all together, the algorithm's overall time complexity is n, as each operation scales linearly with the number of nodes in the tree. Now, focusing on space complexity, the primary factor here is the memory used by the stack during the DFS traversal. The maximum size of the stack depends on the depth of the binary tree, which can vary depending on the tree's structure. In the worst case, such as in a completely unbalanced tree where the tree resembles a linked list, the depth is equal to n, the total number of nodes. This results in a stack size of n. On the other hand, for a balanced binary tree, the depth is proportional to log n, leading to a much smaller stack size of log n. Additionally, the algorithm uses a constant amount of extra memory for variables like original_node and cloned_node, which adds 1 to the space complexity. Therefore, the overall space complexity is h, where h represents the height of the tree. In the worst case, this height equals n, and in the best case, it is log n. Next, let's compare this approach with a brute force method. A naive approach would involve traversing the clone tree independently to search for a node with the same value as the target. While this method still has a time complexity of n, since it requires visiting all nodes in the clone tree, it lacks the efficiency of directly correlating the original and clone nodes during traversal. The space complexity remains h, as the traversal still requires stack memory proportional to the tree's height. However, the current approach is advantageous because it leverages the parallel traversal of the original and clone trees to establish a one-to-one correspondence between nodes. This eliminates the need for separate checks or comparisons based on node values, allowing the algorithm to strictly adhere to the problem constraints while ensuring optimal efficiency. Lastly, considering different scenarios, the best-case situation occurs when the target node is the root. In this case, the algorithm terminates immediately after checking the root, resulting in both time and space complexities of 1. For the average case, particularly in a balanced binary tree, the traversal depth is proportional to log n. While the time complexity remains n, due to visiting all nodes, the stack space used is log n. In the worst case, with a completely unbalanced tree that resembles a linear structure, all n nodes must be traversed, and the stack size grows to n. Therefore, both time and space complexities in the worst case are n. A mathematical proof of these complexities shows that each node is visited exactly once, making the number of operations proportional to n. The stack memory usage, determined by the tree's height, varies between log n and n, depending on the tree's balance. Thus, the time complexity is n, and the space complexity is h, where h is the tree's height. When tackling this problem, there are several common mistakes to watch out for. One is assuming that the original and cloned trees are not identical copies. The problem explicitly guarantees that cloned is a duplicate of original, so comparing values across these trees is unnecessary and only adds inefficiencies to your solution. Another frequent pitfall is neglecting edge cases, such as dealing with empty trees or scenarios where the target node is the root. Forgetting to handle these special cases can lead to runtime errors or incorrect results. Additionally, modifying the structure of the clone tree during traversal, like removing nodes or reassigning pointers, is a major issue. This not only violates the problem constraints but also corrupts the clone tree, making it impossible to validate your solution. Lastly, using recursion without considering the risk of stack overflow can be problematic, especially for unbalanced trees. To avoid this, consider switching to an iterative approach with an explicit stack, which can handle deeper or unbalanced trees more safely. Another mistake to avoid is confusing the traversal order between the original and clone trees. Always ensure that both trees are traversed in the same order, whether it's preorder, inorder, or BFS, to prevent mismatches. Now, a key insight for solving this problem lies in recognizing that the two trees are structurally identical. This means any traversal method that visits nodes in the same order can successfully locate the corresponding node in the clone tree. Techniques like DFS, BFS, or even Morris traversal for inorder can all work here. However, a straightforward DFS or BFS is often the most optimal choice for its simplicity and clarity, with a time complexity of O(n), where n is the number of nodes in the tree. In interviews, it's also helpful to recognize the broader pattern here. This is essentially a variation of tree traversal problems that require locating specific nodes or values. Be prepared for follow-up questions, such as identifying all corresponding nodes that meet a condition, or working with trees that are not exact duplicates but share similarities. This problem has strong connections to other common binary tree problems, which are worth studying to build a deeper understanding. For instance, LeetCode 100, same tree, asks you to determine if two trees are identical. LeetCode 572, subtree of another tree, focuses on checking if one tree is a subtree of another. LeetCode 617, merge two binary trees, involves combining two trees into one, while LeetCode 226, invert binary tree, is often used to practice tree traversal techniques. As for alternative approaches, a recursive DFS is a popular choice due to its simplicity and clear logic, though it may cause stack overflow on deep or unbalanced trees. An iterative DFS using a stack avoids this issue and works well for trees of any depth, though it is slightly more complex to implement. BFS, which uses a queue, is another solid option if you prefer processing the tree level by level, but it does require extra memory for the queue. Lastly, Morris traversal is a space-efficient approach with O(1) additional space, but its complexity makes it unnecessary for this problem, where space optimization is not a primary concern. Great work! Today, we successfully tackled the problem of finding a corresponding node in a cloned binary tree. We reviewed a brute force approach using DFS or BFS and highlighted its importance in navigating tree structures. Keep practicing these traversal techniques, they're foundational for solving many tree-related problems. Thanks for watching, and don't forget to like, subscribe, and stay tuned for more coding solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!